In Episode 18, titled 2.1, Querying Toolkit, Filters, Grouping, Aggregates, and Nested Queries, the focus is querying as the skill of asking precise questions of data, not as the act of writing clever statements. The CompTIA Data DA0-002 exam often tests whether a candidate can reason about what a query is doing and whether the output matches the intent of a business question. Querying is where small misunderstandings become large mistakes because a misplaced filter, a wrong grouping, or a careless aggregate can change totals while still producing results that look neat and numeric. A useful mindset is to treat every query as a claim about scope and meaning, where the query defines what records are included, what comparisons are being made, and what summary is being reported. This episode builds a toolkit of concepts that apply across query languages and platforms, even though the most common vocabulary comes from structured query language, SQL. The goal is clean, predictable reasoning that stays stable under time pressure. Filters are the first tool because they narrow scope, and narrowing scope safely means restricting the dataset without accidentally losing the context needed for correct interpretation. A filter should be read as a rule that defines which records belong to the question, such as a date range, a region, a product category, or a status value. The risk is that filtering can remove records that should remain for comparison, such as removing canceled orders when the question is about total order volume, or removing test records when the question is about system behavior. Another risk is that filters can be applied at the wrong stage, such as filtering after aggregation when the intent was to filter individual records first. Exam stems often hint at scope by specifying a population, a time window, or an inclusion rule, and the correct answer depends on matching the filter to that scope. A careful analyst treats filters as scope declarations and checks whether they match the story the question is trying to answer. Grouping is the tool that turns a single total into a comparison across categories, such as region, product, channel, or time period. Grouping answers questions like which category is higher, which trend is rising, or which segment behaves differently, because it produces one summary per category rather than one summary overall. The critical idea is that the grouped field should represent a meaningful label, and that label should be consistent and clean because messy categories create misleading comparisons. Grouping also interacts with the grain of the data, because grouping a dataset at the wrong level can hide duplication or create false patterns that come from repeated rows. Exam questions often test grouping by describing a desire to compare performance across segments, and the correct reasoning is to group by the relevant dimension while keeping measures in the right place. When grouping is done well, it transforms raw records into decision-friendly summaries without changing meaning. Aggregates must match meaning, not convenience, because the choice of sum, count, average, minimum, or maximum changes what the answer represents. Summing fits measures that add up naturally, such as revenue or quantity sold, while counting fits events or records, such as number of orders or number of customers. Averages can be useful, but they often hide distribution and can be distorted by outliers, which is why an average should be chosen because the question asks for typical value, not because it is easy. Distinct counts are a special case because they count unique entities, such as unique customers, and they behave very differently from counting rows, especially after joins. Exam stems often describe goals like total sales, average order value, or unique visitors, and each goal implies a different aggregate that must align with what is being measured. Choosing the correct aggregate is one of the most common points lost on data exams because a wrong aggregate can look reasonable while answering a different question. Mixing row-level and summary-level logic incorrectly is a classic error because it blends two different kinds of statements about data. Row-level logic describes conditions about individual records, such as orders where status equals shipped, while summary-level logic describes conditions about groups, such as regions where total revenue exceeds a threshold. When these are mixed, the result can include or exclude records in ways that do not match intent, such as filtering out individual records when the real intent was to filter groups after aggregation. Another common mistake is applying a condition to an aggregate as if it were a condition on each row, which produces confusion and wrong totals. Exam questions sometimes describe a need like, show regions with more than 1,000 orders, and the intended skill is recognizing that the condition applies to group totals, not to individual orders. Keeping row-level thinking separate from group-level thinking prevents these mistakes and makes reasoning about results far easier. Nested queries are useful because they simplify complex, multi-step questions by breaking them into stages that can be reasoned about separately. A nested query can be thought of as producing an intermediate data set that becomes the input to another step, allowing the analyst to handle filtering, grouping, and calculations in a clear sequence. This supports clarity when a question requires multiple transformations, such as finding the top products per region and then summarizing those results at a higher level. Nested queries also reduce repetition because an intermediate result can be reused without rewriting logic, which reduces the chance of inconsistent conditions. Exam stems sometimes include multi-part requirements that are hard to satisfy in a single flat statement, and nested logic is often the cleanest conceptual answer. The key is not the syntax, but the idea of staged reasoning, where each stage has a defined input, a defined operation, and a defined output. Reading queries left to right, then verifying intent, is a simple discipline that reduces errors and improves speed. Reading left to right means following the flow of what is selected, what source it comes from, what conditions apply, how groups are formed, and what calculations are produced. After reading, verifying intent means restating in plain language what the query is claiming, such as, this returns total revenue per region for the last quarter, and checking that the pieces actually match that claim. Many errors are visible at this stage, such as noticing that a date filter is missing, that a join will duplicate rows, or that an aggregate is applied to the wrong field. On the exam, this skill helps because it prevents being fooled by answers that look technical but do not match the STEM's required output. Verification is where correctness becomes deliberate rather than accidental. Null handling is a quiet pitfall because nulls behave differently in filters and counts, and small misunderstandings can change results. A filter that checks equality may exclude nulls in ways that are not obvious, which can remove records that should have been included when null represents unknown or not yet filled. Counts can also be tricky because counting a field may ignore nulls, while counting rows counts all records, and that difference can matter when completeness is being measured. Distinct counts can be affected as well, because null may or may not be treated as a distinct value, depending on the system, and assumptions here should be consistent and understood. Exam stems sometimes mention missing data, optional fields, or incomplete records, and those cues are often a signal that null handling matters to the correct answer. A safe habit is to be explicit about how nulls should be treated, and to interpret results with awareness of what nulls represent in the scenario. A sales example provides a stable way to practice grouping and totals because sales data contains both measures and categories. Imagine a data set where each record represents one order line with fields like region, product category, quantity, and line revenue, And the question is to compare total revenue by region. Filtering might restrict the time frame to a specific month. Grouping would use region, and summing would use line revenue to produce totals that match the business meaning. If the question changes to unique customers per region, the aggregate must shift to a distinct count of customer ID, and that choice changes the output dramatically, even though the table looks similar. If a join adds product attributes, the join must be checked so it does not multiply order lines, because multiplication would inflate revenue totals. This example shows why aggregates and joins must match grain and meaning, and it mirrors the kind of reasoning the exam expects. Readability matters because a query that cannot be understood cannot be trusted, and trust is the hidden requirement behind most querying work. Clear names and consistent style make it easier to spot errors, easier to review, and easier to modify without breaking logic. Consistency includes using clear aliases, using consistent capitalization and formatting, and keeping expressions simple enough that intent is visible. Readability also supports auditability because a reviewer can trace how a result was produced and can confirm that filters and aggregates match stated requirements. Exam questions sometimes contrast approaches that are technically equivalent, and the better choice is often the one that is clearer and less error-prone. A calm rule is that clarity is part of correctness, because unclear work is difficult to verify and therefore difficult to trust. Small sample checks protect against large-scale mistakes because they validate logic before it is applied to full datasets. A small sample can reveal whether filters are selecting the intended records, whether joins are matching correctly, and whether aggregates behave as expected. Sampling also makes it easier to spot subtle issues like duplicated rows, unexpected nulls, or mistyped fields that break grouping categories. In professional practice, a quick, small check often saves hours of debugging because it catches problems before results are communicated. Exam stems sometimes describe a scenario where results do not match expectations, and the correct reasoning includes verifying logic with controlled checks rather than blindly trusting the first output. The key concept is that queries are hypotheses, and sampling is a quick way to test those hypotheses. Performance tuning often begins with limiting columns and rows early, because reducing the amount of data processed reduces work for the system. Pulling only needed columns reduces memory and I/O overhead, and filtering early reduces the number of rows that must be joined and aggregated later. This matters especially when datasets are large or when queries run repeatedly in reporting contexts, because small inefficiencies can become recurring costs. Indexes and partitioning can help in many systems, but the exam usually emphasizes the more general principle that scope reduction improves performance and also clarifies intent. A query that selects everything and filters later is both slower and harder to reason about, which increases the risk of mistakes. The practical recall point is that performance and correctness often align when scope is made explicit early. A short mental model for query building keeps the toolkit usable under time pressure by turning query work into a predictable sequence of decisions. First, name the question in plain language and identify the population and time window, because that defines the base scope and filters. Next, identify the grain of the base data and the grain of the desired output, because that determines grouping and whether joins will multiply rows. Then, choose the measure and the aggregate that match meaning, such as sum for additive measures or distinct count for unique entities. After that, add grouping labels, apply necessary joins carefully, and verify that null handling and missing matches behave as intended. Finally, restate the query's intent in one sentence and confirm that the output columns support that intent without extra noise. This sequence is simple enough to remember and detailed enough to prevent the most common errors. To conclude, a 5-minute query rehearsal today can be as simple as speaking a question, naming the filter, grouping and aggregate choices, and then stating one pitfall to check before trusting the result. Filters control scope. Grouping controls comparison. Aggregates control meaning. And nested stages help manage complexity when requirements stack up. Separating row-level logic from group-level logic prevents subtle errors, and careful attention to null handling prevents silent shifts in counts and totals. Readability and small sample validation protect trust, while limiting columns and rows early protects performance and often improves clarity at the same time. The most useful habit is to restate what a query returns in plain language and then verify that every clause supports that statement, because that aligns query work with the exam's emphasis on intent. Choose one sales-style question, save the intended output aloud, and rehearse the filter, grouping, and aggregate decisions once, because that small repetition builds a reliable reflex. Choose one sales-style question, say the intended output aloud, and rehearse the filter, grouping, and aggregate decisions once, because that small repetition builds a reliable reflex. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.